Hello my friends and welcome back to the You Can Do TV channel. The sugarcane bagasse pulp molded tableware industry is rapidly expanding, driven by increasing demand for sustainable and eco-friendly alternatives to plastic. Sugarcane bagasse, a byproduct of sugar production, is an abundant and renewable resource, with approximately 600 million tons of bagasse produced annually worldwide. This industry converts bagasse into biodegradable tableware such as plates, bowls, and trays, using high-temperature molding and water-based binding agents. The global market for molded fiber packaging, including bagasse tableware, was valued at approximately $4.2 billion in 2023 and is projected to grow at a CAGR of 6.5% to reach $6.4 billion by 2030. A significant driver of this growth is stringent environmental regulations and bans on single-use plastics in regions like the European Union and India. Bagasse tableware production is energy efficient and sustainable, requiring 30 to 50% less water and energy compared to plastic manufacturing. Each ton of bagasse used can prevent the emission of 1.5 tons of CO, contributing to reduced carbon footprints. Fully automatic compostable sugarcane bagasse pulp molding food containers packaging making machine is a state-of-the-art solution for producing environmentally friendly tableware and packaging. Its operation comprises three main stages. Hot pressing stage. In this stage, the pre-formed pulp molds are subjected to heat and pressure to solidify and shape the products. The precise temperature and pressure parameters ensure uniform thickness, durability, and smooth surface finishing, making it ideal for items with complex structures like chocolate trays or deep food containers. Trimming stage. After hot pressing, the formed products are trimmed to remove excess material, ensuring clean edges and a polished appearance. This automated trimming process enhances efficiency and reduces waste while maintaining the structural integrity of the final product. Automatic stacking plus conveying weighing. The trimmed products are automatically stacked and conveyed for weighing and packaging. This stage ensures consistency in the number of items per stack and provides quality control by verifying the weight. The automated system reduces manual handling, enhancing production speed and reliability. This machine supports sustainable production by using raw materials like sugarcane bagasse, bamboo fiber, and wheat straw fiber, creating a wide range of compostable food containers and tableware. A group of students in Egypt has developed an innovative technique to integrate sugarcane bagasse ash, SCBA, into the construction industry, offering an eco-friendly solution to a pressing environmental challenge. Sugarcane waste, often burned or dumped illegally into the Nile or landfills, produces over 2 million tons of carbon dioxide emissions annually in Egypt. This initiative aims to repurpose the residue into concrete, reducing hazardous emissions while promoting sustainable construction practices. The process begins by collecting sugarcane waste from local juice shops, drying it, and grinding it into a fine powder. To mitigate the environmental impact of burning, the team employs a controlled oxygen-free environment, minimizing carbon emissions. The resulting ash is then incorporated into concrete mixtures, replacing up to 10% of traditional Portland cement, which is responsible for a significant portion of global carbon dioxide emissions. Extensive research and experimentation over 4 months demonstrated that concrete blocks containing SCBA exhibited comparable, and in some cases superior, strength to standard blocks. By replacing a portion of Portland cement, the technique not only reduces reliance on traditional materials but also curtails the construction sector's carbon footprint, which contributes over 40% of global emissions. This innovative approach underscores the potential of waste-to-resource strategies to revolutionize construction while addressing critical environmental concerns. The process of developing high-yield sugarcane varieties involves several stages of careful selection, breeding, and testing. Initially, researchers identify desirable traits such as high sucrose content, disease resistance, and adaptability to local growing conditions. Crossbreeding is then conducted between parent plants with complementary traits to create genetic diversity. Through successive generations, selections are made based on the expression of desired characteristics. Field trials are conducted to evaluate the performance of promising varieties under real-world conditions, including assessments of yield, disease resistance, and agronomic traits. Those with the highest yields and overall performance are further refined through selective breeding and testing. In the next section, we will visit the sugarcane growing area in Sembilan, Malaysia. With an area of 138.6 hectares, this sugarcane growing area produces 2,816 tons with an economic value of about Rm 4,694 million. Sugarcane planting involves several stages and techniques to ensure optimal growth and yield. Here's a detailed description of the sugarcane planting process. Planting area preparation. The first step in sugarcane planting is preparing the planting area. This involves loosening the soil and building furrows. The distance between the furrows is typically 1.5 meters, while the distance between individual plants within the furrows is 1 meter. Selection and preparation of plant material. Sugarcane is typically propagated using stem cuttings or shoot cuttings, each containing 3 to 4 buds. These cuttings are planted in the furrows, usually in opposite directions, to promote better growth and support among the plants as they mature. Soil management during growth. As the sugarcane plants grow, soil is piled up around the base of the plants and compacted. This practice helps support the plants and prevents them from collapsing. The soil is periodically checked and maintained to ensure proper support for the growing sugarcane. Watering and irrigation. Sugarcane requires regular watering, especially during its initial stages of growth. Typically, it is watered once a day to maintain soil moisture levels. Adequate irrigation is essential for optimal growth and development of the sugarcane plants. Fertilization. Fertilization is crucial for providing essential nutrients to the sugarcane plants throughout their growth cycle. Different fertilizers are applied at specific intervals. NPK 15 hours 15 minutes and 15 seconds fertilizer is applied at a rate of 250 kilograms per hectare in the first and third months. Urea is applied at a rate of 125 kilograms per hectare in the third month. NPK 15 hours 15 minutes and 15 seconds fertilizer is again applied at a rate of 300 kilograms per hectare in the fifth month. Pruning and disease control. Regular pruning is performed to remove old leaves, retaining only 8 to 10 healthy leaves per plant. This practice helps control the spread of diseases such as warstripe disease, which can affect sugarcane crops. Pesticides are applied as necessary to control pests and diseases, ensuring the health and productivity of the sugarcane plants. Harvesting. Sugarcane is typically ready for harvesting approximately 7 to 10 months after planting, depending on various factors such as climate and soil conditions. The estimated yield per hectare ranges from 56 to 60 tons, with corresponding gross income estimated at Rm 2,000, 4,000 per hectare. Once the sugarcane reaches maturity, it is harvested and prepared for sale in the market. By mechanizing the planting process, the sugarcane billet planter offers significant advantages to cane farmers, including reduced overhead costs and increased operational efficiency. This not only streamlines the planting process but also enhances overall crop yield and profitability for farmers, making it a valuable asset in modern sugarcane cultivation. The process begins with field preparation, ensuring that the soil conditions are optimal and the spacing between furrows is appropriate for the sugarcane crop. Billets, which are small sections of sugarcane stems, are loaded into the planter's hopper, ready for distribution. Once loaded, the planter efficiently distributes the billets along the furrows with precision, ensuring uniform spacing to promote optimal growth and development. As the planter advances, it automatically plants the billets into the soil at the desired depth, completing the planting process seamlessly. The sugarcane deep planter revolutionizes sugarcane plantation with its efficient and multifunctional design. Starting with seedling preparation, the machine simplifies the process by automatically cutting long sugarcane stems to a standardized length, typically exceeding 30 centimeters. This ensures uniformity in seedling size, crucial for consistent growth. Moving to the planting phase, the machine grooves the soil and inserts the seedlings at a stable depth, usually between 20 to 25 centimeters. This consistent planting depth promotes even root development and optimal growing conditions, leading to healthier plants and higher yields. Simultaneously, the machine fertilizes the planted seedlings with precision. Utilizing a rust-resistant stainless steel tank, it applies fertilizer near the stems, minimizing waste and promoting initial growth. Upon completion of planting and fertilization, the machine compresses the soil around the seedlings, ensuring stability and optimal root-soil contact. This step is essential for nutrient uptake and overall plant health. Operators can customize parameters like soil coverage and roller pressure to suit specific field conditions, while key components are built for long-lasting performance. Watering technology plays a pivotal role in sugarcane cultivation, especially in regions like São Paulo and Goiás, where climate change-induced water deficits challenge production. With up to 70% of losses attributed to water deficits, addressing this issue is critical. Innovative irrigation methods have emerged as a solution, significantly impacting productivity. The integration of irrigation with sugarcane production systems has led to substantial advancements. Initially piloted over 40 hectares, the positive results spurred further investment in larger areas. Improved productivity and verticalization of production became key objectives. Drip irrigation stands out as a leading technology due to its operational ease and efficiency. By precisely delivering water and nutrients to plants' roots, it optimizes resource use and enhances crop health. Fertigation, the combined application of water and nutrients, further enhances efficiency throughout the crop cycle. Subsurface drip irrigation, in particular, offers flexibility and efficiency, allowing for meticulous water and nutrient management. Its implementation across extensive areas has shown remarkable results, with notable gains in productivity and cost-effectiveness. Moreover, sustainability is a cornerstone of modern irrigation practices. Efforts such as utilizing vinasse for fertigation and recycling water from filter backwash demonstrate a commitment to resource conservation and environmental stewardship. Sugarcane burning is a contentious agricultural practice employed primarily for pre-harvest preparation. The main reasons for its use include pest control, removal of leafy matter, and facilitation of manual harvesting. By burning the fields, farmers effectively eliminate pests and their habitats, reducing the need for chemical pesticides. Additionally, burning removes excess foliage, making it easier for workers to access and cut the cane during harvesting. Furthermore, burning assists in the removal of dead leaves, which can impede the processing of harvested cane. Without burning, these leaves would need to be mechanically removed, increasing labor and machinery costs. While there are alternatives such as green harvesting or mechanical cutting, they may not be as cost-effective or practical in certain regions. Despite its benefits, sugarcane burning also has significant environmental drawbacks, including air pollution, soil degradation, and biodiversity loss. The cane lifter is a revolutionary machine designed for harvesting sugarcane efficiently and economically. Powered by cutting-edge technology and control systems, it stands out in the market for its low fuel consumption and high operational performance. With a remarkable lifting capacity of 800 kilograms per load and a total weight lifting capacity of 1,500 tons per day, it's capable of navigating through wet terrain without damaging furrows, reducing compaction by 32%. This ensures both productivity and sustainability in the harvesting process. The integrated operator's cabin is a standout feature, allowing for a 185-degree rotation with the arm to load from both sides. Equipped with air conditioning for operator comfort and optimal visibility, it ensures smooth operation even in challenging conditions. Ergonomic joystick controls further reduce operator fatigue while ensuring precise and controlled movements of the arm. The transmission system, featuring hydrostatic power on all four wheels, adjusts power according to terrain conditions, enhancing maneuverability and efficiency. Cane harvesters are specialized machines designed for efficiently harvesting sugarcane. The process begins with the harvester's sharp blades cutting the sugarcane stalks near the base. These blades are attached to rotating drums or discs, which swiftly sever the cane from the roots. As the machine moves forward, the harvested cane is conveyed into the harvester through a series of rollers or belts. Inside the harvester, the cane passes through cleaning mechanisms that remove excess leaves, debris, and dirt. Then, it's typically chopped into smaller pieces to facilitate handling and transportation. Some harvesters also have systems to separate trash and other impurities from the harvested cane. Modern cane harvesters are often equipped with advanced technology, including GPS systems and sensors, to optimize harvesting efficiency and accuracy. These technologies help the harvester to navigate the field precisely and adjust its operations based on real-time data. At the mill, sugarcane is weighed and sampled to control input quality. The excavator shovels the raw material cane and pour it into the milling line. A series of many mills compresses the sugarcane fibers and separates the juice from the bagasse, which can be used later as a fuel source. The initial juice is dark green in color and is acidic and turbid. The milling process typically begins with the crushing of the cane using heavy rollers, which separate the juice from the fibrous material. The juice is then collected and passed through a series of screens and filters to remove any remaining solids. This process produces sugar juice and bagasse, the dry, pulpy residue left after the juice is extracted. The juice is collected in large vats and the concentration is measured. Steam is used to heat and evaporate the cane juice. Steam plant provides the necessary energy to power the various stages of the sugar production process. In this step, lime is added to the extracted juice, which is then heated to remove impurities. The lime neutralizes acids and precipitates impurities in large vessels called clarifiers. The clear sugar juice is run off the top of each clarifier. The aim of filtration is to remove any impurities from the sugar syrup, resulting in a clear and pure final product. This involves the removal of excess water from the sugar syrup to create a thick, concentrated syrup that is then processed into sugar crystals. After the cane juice is extracted from the cane and purified, it is heated in a series of vessels, known as evaporators, to evaporate the excess water. The clear juice is concentrated by boiling under a vacuum into a syrup. The syrup is further concentrated and seeded with small sugar crystals. The sugar crystals then grow to the required size. Once they reach the correct size, the crystals and remaining syrup are discharged from the pan. The syrup and crystals are separated by spinning at high speeds in centrifugals. The dark syrup is thrown off and passes through perforations in the machine. The spin-off syrup is boiled down again, often multiple times, to get the maximum number of crystals. The final syrup is molasses. The crystals are dried by tumbling them through a stream of hot air in a rotating drum. The damp sugar crystals are dried in large, hot air dryers, reaching a moisture content of as low as 0.02%. Next, the sugar is gently tumbled through heated air in a granulator. The dried crystals are then separated into different sizes through vibrating screens and placed into storage bins. The sugar produced from a sugar mill is not food grade. The raw sugar from a mill must go through a refining process until it is suitable for human consumption. True Shiitake, a brand dedicated to cultivating shiitake mushrooms, takes a unique and sustainable approach by growing these delectable fungi on wood. The process begins with the careful selection of oak wood. The chosen oak wood serves as the substrate for shiitake cultivation, but the versatility of this wood decay fungus allows it to thrive on various types of wood, excluding conifers. The wood's hardness and the amount of sapwood present influence the quantity and duration of the fungal production. In spring, the cut logs undergo a drilling process, creating tight, regularly spaced clamps. The oaks were harvested during the winter season when the trunks are rich in nutrients, especially sugars. These sugars play a crucial role in fueling the later growth of the shiitake fungus. These drilled holes are then filled with specially prepared planting material containing mycelium, carefully selected over several years to ensure successful fruiting in the given climate. This sets the stage for the optimal colonization of the wood by the shiitake fungus. The inoculated trunks are then stored under optimal conditions for a period of 6 to 12 months, during which the entire organism grows and matures. Full colonization becomes evident in the trunk cuts. Regular soaking follows, leveraging the unique relationship between shiitake and water to control the production timeline. After full colonization, the strains are soaked in water to initiate the formation of fruiting bodies, resembling a larger-scale version of the traditional box move. Within 3 to 5 days after soaking, the first tiny primordia of future mushrooms appear and continue to grow, subject to temperature and other conditions. The cultivation process integrates with the production of firewood, allowing for the dual-purpose use of the resource. This approach supports a unique combination of intensive and extensive farming, producing up to 30 times more protein on a few hundred square meters compared to traditional cattle farming, with significantly lower water requirements. The journey of true shiitake began in the USA, where the founders experimented with inoculating fallen oak trees with mycelium using a successful Japanese method. Despite the challenges of adapting to the Labe region's climate, true shiitake continues its mission to grow quality, healthy mushrooms with respect for nature and a commitment to promoting human health. Champion's Charlevoix has perfected the art of cultivating fresh oyster mushrooms, defying seasonal limitations. The innovative process, born from 8 years of dedicated research, involves boiling wood for 8 hours, significantly expediting the growth cycle. This method ensures a consistent and reliable weekly mushroom supply. Daniel Louis Garneau, the driving force behind the operation, has ingeniously crafted products that capture the forest's essence, from pesto to wild chanterelles. What sets Champion's Charlevoix apart is not just their commitment to sustainable practices but also their ability to transform delicate mushrooms without the use of additives or chemicals. The result is a culinary adventure that harmonizes nature's bounty with a mastery of flavor, bringing a taste of the wild to every table. At Northway Mushrooms, the art of cultivating quality mushrooms begins with the meticulous process of crafting mushroom compost. The journey starts at the compost yard, where a blend of essential ingredients is combined to create the perfect growing medium. The key components include wheat straw, water, chicken manure, and gypsum. The first step involves soaking the wheat straw in water, ensuring it reaches the optimal moisture level. Simultaneously, chicken manure is carefully mixed with gypsum to enhance its nutrient content. These ingredients then find their way into a specially designed mixer, where they are blended to form a homogeneous mixture. The resulting mixture is moved into large composting piles, setting the stage for the crucial next phase, aerobic fermentation. This natural, oxygen-dependent process initiates a chemical reaction within the compost, generating heat. As temperatures rise, the compost must be regularly turned and watered to prevent it from exceeding 80 degrees Celsius, ensuring an ideal environment for the mushroom mycelium to thrive. After the compost undergoes this meticulous conditioning, it is funneled into rows for pasteurization. Over the course of 12 days, the straw transforms, becoming softer and adopting a rich chocolate brown hue. The compost is then transferred to a special polytunnel for heat treatment, a process known as pasteurization. During pasteurization, controlled air is utilized to heat and cool the compost, effectively eliminating unwanted bugs and bacteria. This rigorous sterilization ensures a clean and optimal environment for mushroom growth. The compost is now ready for the final step, integration with mycelium. The mycelium, contained in grain, is mixed into the compost. This marks the beginning of the growth phase, where the mycelium establishes roots within the nutrient-rich substrate. Once the mycelium takes hold, the compost can be delivered in the form of blocks or by bulk load, ready to support the flourishing of high-quality mushrooms. The process at Northway Mushrooms guarantees a product that is not only clean and sterile but also primed for the successful cultivation of exceptional fungi. The journey of growing and picking mushrooms at the farm begins with the arrival of carefully crafted compost. This nutrient-rich substrate is loaded into the mushroom tunnel, laying the foundation for a cultivation process. Casing, a crucial element for mushroom formation, arrives next. It serves as a protective layer, holding water and safeguarding both the root system and mycelium. With precision, a 5 cm layer of casing is applied onto the compost surface. The peat is then gently ruffled, stimulating growth and preparing the substrate for the upcoming stages. To create an optimal environment, the casing is watered down and the temperature is maintained at a consistent 25 degrees Celsius. As the weeks progress, a carefully orchestrated manipulation of temperature and fresh air introduction occurs, sparking the formation of mushrooms. Approximately 2 weeks after the compost is initially filled, the first flush of mushrooms emerges. Harvesting becomes a delicate task, requiring careful handpicking. The mushrooms are harvested by cutting the roots and placing them into punnets. Once picked, the mushrooms are promptly moved into refrigeration to maintain freshness until ready for collection. Watering is essential between flushes, and a second flush of mushrooms appears about a week later. The process repeats on the third week, yielding yet another flush of mushrooms. As the cycles progress, the compost gradually wears out and must be removed. Maintaining cleanliness and tidiness is paramount in mushroom production. After each harvest, everything in the mushroom tunnel is thoroughly washed. This rigorous hygiene routine is crucial for preventing diseases from infiltrating the crop. The tunnel undergoes sterilization and steaming, preparing it for the introduction of new compost. The entire growing process, from the arrival of compost to the completion of a harvest cycle, spans 6 weeks. Upon arriving at the pack house, mushroom temperatures are swiftly assessed for freshness. Advanced automated packing lines efficiently handle the meticulous packaging process, incorporating thorough quality checks. Punnets, housing the mushrooms, undergo precise weighing, wrapping, and labeling, preparing them for dispatch. Barcodes are generated, printed, and affixed to corresponding orders, streamlining the tracking process. The labeled punnets proceed to the loading bay, where orders are systematically processed for distribution. In response to the growing challenges faced by mushroom growers in the hand-picking process, Van den Top introduces a groundbreaking solution for the mushroom fresh market, the semi-automatic picking bridge. This latest patented product is designed to enhance hand-picking performance by an astounding 300%, offering a significant leap in efficiency for mushroom harvesting. The system is equipped with a fully automated weighing system and drainage, providing a comprehensive solution for mushroom growers. Over the past 2 decades, manual picking has increasingly become a hindrance in the mushroom industry, with the difficulty of securing labor for harvesting becoming a prominent issue. Recognizing the need for equipment to assist in hand-picking, Van den Top embarked on a mission to create a solution that not only addresses the labor shortage but also significantly improves the efficiency of the entire process. Van den Top's semi-automatic picking bridge is a revolutionary product tailored for the fresh market. The focus is on a one-layer system designed to fit seamlessly into existing shelving systems. While this approach may require slightly more space, the benefits far outweigh the costs. The system's design ensures that the initial investment is quickly recouped through a substantial increase in picking efficiency. Results from extensive testing have demonstrated that individuals using the semi-automatic picking bridge can pick 2.5 to 4 times faster compared to traditional hand-picking methods. The machine enables users to pick at a rate of 140 mushrooms per minute, translating to a remarkable 8,400 mushrooms per hour. This speed is achieved without compromising the careful handling of the mushrooms. The machine is designed to be easily operated by individuals, allowing for a smooth transition to the new picking process. Depending on the pace at which people can or may work, the semi-automatic picking bridge accommodates flexibility by allowing the use of 2 to 3 individuals simultaneously. Sugarcane cultivation often faces significant challenges due to low-quality water and soil, both of which can adversely affect yield and profitability. The installation of a subsurface drip irrigation system offers a transformative solution to these issues. By integrating Netifum's advanced irrigation room and subsurface drippers, farmers gain precise control over water pressure and flow rates, ensuring water and nutrients are delivered directly to the root zone where they are needed most. Subsurface drip irrigation is engineered for efficiency and sustainability. The system adapts to the crop's growth stages, allowing tailored delivery of water and nutrients to optimize plant development. This not only boosts crop yield but also significantly increases sucrose content, a key metric for sugarcane quality. Unlike traditional irrigation methods, subsurface systems remain intact during harvest, eliminating the need for costly labor and equipment setup for subsequent growing cycles. The benefits of switching to subsurface drip irrigation are striking. Average yields with this system can be up to 50% higher than those achieved with sprinkler systems or flood irrigation, and up to 200% higher compared to rain-fed plantations. Moreover, optimal water and nutrient delivery reduces plant stress, significantly extending ratoon life. Farmers can expect an average of 8 to 10 cuts per planting cycle, maximizing the economic value of their crops. Netafim's innovative approach has helped irrigate over 550,000 hectares of sugarcane worldwide. The system is also environmentally sustainable, offering water savings of up to 50% while improving nutrient use efficiency by up to 30%. Additionally, reduced labor costs and a potential yield increase of up to 180 tons per hectare make this technology a game-changer for sugarcane farming. With over 40 years of experience in sugarcane irrigation, the solutions have proven their value to farmers across the globe. By adopting subsurface drip irrigation, growers can produce more cane, improve sugar recovery, and secure long-term sustainability in their operations. This innovative method exemplifies how modern technology can address traditional agricultural challenges, ensuring better outcomes season after season. Refined sugar starts as non-food grade raw sugar. The first step in the refining process is receiving raw sugar from one of the Mackay mills. The load arrives by truck and is tipped into an automated unloading hopper that's connected by conveyor belt to the refinery's 1,000-ton holding bin. The raw sugar is delivered to the refinery at a rate of 55 to 60 tons per hour. The refining process begins when raw sugar is mixed with hot concentrated syrup known as raw wash. This mixture is known as magma and its density is closely controlled before it's put through the centrifuge, where it's spun at rates exceeding 1,000 revs per minute. When the crystals are spun at high speeds, the sugar and syrup separate. To help this process, hot water is sprayed onto the magma, forcing the syrup and impurities through the tiny holes in the screen. What remains are fine raw sugar crystals. An added benefit of this process is the removal of around 30% of the color from the original raw sugar crystal. The affined raw sugar is dissolved in hot water at 8 degrees to form melter liquor. The sugar content of this liquor is about 65%. The liquor is then passed through a coarse screen to remove large particulate matter. The next step is the clarification process known as phosphatidation. This is where lime and food-grade phosphoric acid are added to the melter liquor. Fine bubbles of air are introduced, along with a flocculant. This helps bind the impurities together and float them to the surface of the clarifier vessel. This floating layer is known as scum. Once it's removed, workers are left with clarified liquor. The clarifying stage is critical in the refining process as it's where most of the impurities are removed from the liquor stream. The next stage involves the clarified liquor being heated further, then put through sand and gravel filters before being sent to the activated carbon columns. The activated carbon columns are where the majority of color is removed from the liquor. The carbon works much like a fish tank filter. It removes organic and other residual material, resulting in a further 85% color removal. Liquor color is one of many parameters closely monitored by the refinery lab staff. Based on lab results, small adjustments are made to factory parameters to ensure the refinery produces a consistent quality product that is always in spec. Sugar Australia's Mackay and Yarraville refineries produce some of the best quality food-grade sugar in the world. Once the liquor is passed through the carbon columns, it is known as fine liquor. Excess water is then removed from the liquor by passing it through a triple effect evaporator. This concentrates the liquor from 65% sugar content to 78% sugar content in an energy-efficient way. From here, the liquor is moved to vacuum pans where it is seeded with CSR castor sugar to grow the sugar crystals. This automated process produces batches of sugar crystals that are consistently the desired size. The thick sugar syrup mix known as masaki now moves to the final centrifuge where it is spun at speeds in excess of 1000 revs per minute. The refined fugels remove the syrup from the mix. The amount of wash water added to the mix during the spin cycle will dictate the final color of the sugar crystals. The syrup is either returned to the pans to grow more sugar, or is used to make CSR branded raw sugar, castor raw sugar, coffee sugar, or demerara sugar. The food-grade sugar manufacturing process is almost complete. The sugar crystals are now sent to a large rotary dryer where warm dry air is used to remove excess moisture. The dried sugar is then air-conditioned and dehumidified in a 3,000-ton conditioning silo. The final product remains in the silo for 24 to 36 hours. Next, we'll visit Nestlé's KitKat factory to explore the process of producing delicious KitKat bars. The delightful aroma of freshly baked wafers fills the factory as they are prepared for KitKat production. These wafers, a key component of the beloved chocolate bars, are baked with care on site. They're not just an ingredient. These wafers are so delicious on their own that they could be enjoyed as a standalone treat. After baking, they're delicately coated with a special sandwiching cream, a secret formula that adds an extra layer of flavor to the KitKat experience. Robotic precision comes into play as the wafers are stacked with utmost care and speed. Two robots are at the ready to insert the perfectly assembled wafers into KitKat molds. Once in the molds, a cascade of rich chocolate is poured over the wafers, ensuring each one is fully coated. Excess chocolate is expertly removed, leaving behind a smooth surface that completes the iconic KitKat shape. The finished bars move swiftly down the production line, packaged one after another at an impressive pace. To maintain the integrity of the chocolate coating, the room temperature is kept lower than usual. Before they're ready for distribution, each KitKat undergoes a thorough quality check using X-ray inspection equipment and cameras. Only those that meet the highest standards are deemed fit for delivery to eager customers worldwide. The art of chocolate making has been perfected to an exceptional level by the Canonica chocolatier in Geneva, Switzerland. The Canonica family has been producing chocolates for over 3 generations, and their passion for chocolate is reflected in their exquisite creations. The Canonica Chocolatier Workshop is a place of magic, where every step in the chocolate making process is done with precision and care. Each chocolate is made by hand, using only the finest ingredients and the highest quality cocoa beans. The chocolatiers take great care in selecting the right beans, roasting them to perfection, and blending them into unique and delicious flavors. The process of making chocolate at Canonica Chocolatier is a time-honored tradition. The chocolatiers start by carefully grinding the cocoa beans to create a fine chocolate paste. Then, they add sugar, milk, and other ingredients to create a smooth and creamy texture. The chocolate is then molded into various shapes and sizes and decorated with delicate designs and patterns. The Canonica Chocolatier creates a wide range of chocolate products, from the classic bars to truffles, pralines, and filled chocolates. Their unique flavors range from the traditional milk chocolate to the more exotic, like jasmine, passion fruit, and lavender. One of the most popular products of Canonica Chocolatier is their signature chocolate chess set. This set is a true work of art, made entirely of chocolate, and includes 32 chess pieces and a board. Each piece is handcrafted and hand-painted, and the set is presented in a beautiful wooden box. Another specialty of Canonica Chocolatier is their Chocolate Academy, where they offer workshops and classes for chocolate lovers who want to learn the art of chocolate making. The classes cover various topics, from chocolate tempering to truffle making, and are taught by the expert chocolatiers of the Maison Canonica. Smarties are a popular candy brand produced by Nestlé. The candy is characterized by its colorful sugar coating and chocolate center. The production of Smarties involves several steps, and Nestlé has released B-roll footage that provides an inside look into the manufacturing process. The B-roll footage shows the raw materials used in the production of Smarties. The chocolate center is made from cocoa, sugar, milk, and other ingredients. The colorful coating is made from sugar and food coloring. The ingredients are carefully measured and mixed in large vats to create the candy mixture. The candy mixture is then poured into molds, which are shaped like the familiar Smarties discs. The molds are then cooled to allow the candy to solidify. Once the candy has solidified, the molds are opened and the Smarties are released. The B-roll footage also shows the packaging process. The Smarties are sorted by color and placed into tubes or bags, depending on the packaging type. The packaging is carefully sealed to ensure the candy stays fresh until it reaches the consumer.